Welcome back to AI Paper Podcasts. Okay, so imagine you're an AI engineer, right? You're designing a cutting-edge LLM system. You've loaded it up with, say, 100 crucial instructions, specific formats, key terms, maybe compliance rules. How many of those instructions do you actually think it can remember and follow consistently? It's a fascinating question.
It really is. And it's absolutely critical. That's the core question we're digging into today, based on a really pivotal paper. It's titled, How Many Instructions Can LMS Follow at Once? Authored by Daniel Jaroslavich and the team over at Distill of AI.
Right. And it tackles this problem that, feels really relevant for anyone working with LLMs in production.
Exactly. These systems are increasingly expected to handle, dozens, sometimes even hundreds of instructions all at the same time.
And the current benchmarks, they just don't really test that, do they? They're usually focused on maybe one or just a few instructions.
That's the gap. Yeah, we don't have a great understanding of how these models cope under that kind of high cognitive load.
Which, as you know, can lead to real problems. Chatbots making things up, giving bad advice. These aren't just small glitches. They can have serious operational, even legal consequences.
Absolutely. So to address this, the researchers developed IFScale. It's actually quite a simple idea, but really powerful as a benchmark. It's designed specifically to measure how that instruction following ability degrades as you pile on more and more instructions.
And how did they test it? What was the task?
They used a business report writing task. The models had to generate a report while including up to 500 specific keywords. Those keywords were the instructions.
Wow, 500. Okay. So before we really get into the weeds, maybe let's do that quick summary, the kind of 1-minute version of the key insights for everyone listening. All right, first off, even the best, the frontier LLMs, they really struggle with these high instruction loads. Think only about 68% accuracy at the max density of 500 instructions. It's not great.
Not great at all. And they break down in different ways. The paper identifies 3 distinct patterns. There's a threshold decay for reasoning models. They're fine, then boom.
Okay.
Then a linear decay for some others, just a steady decline. And finally, an exponential decay for some models, where performance just plummets really quickly and bottoms out, sometimes as low as 7 and 15% accuracy.
Yikes. And what about the order of instructions? Does that matter?
It does, but it's complicated. There's a primacy effect. They tend to follow earlier instructions better. But, and this is the really interesting part, that bias actually fades away at super high densities. It suggests they just get overwhelmed.
Right, and when they fail?
Overwhelmingly, they commit omission errors. They just leave the instruction out entirely, rather than trying to modify the words slightly.
And the final key point.
Accuracy versus speed. Reasoning models.
Yeah.
Generally more accurate under load, yes, but their latency can go way, way up. So there are some critical efficiency trade-offs you need to consider.
Okay, great summary. So our mission for the rest of this chat is to really unpack all of that, understand these nuances, how the models behave under pressure, and what it means for you when you're actually building and deploying these systems. Should be some real aha moments, I think.
Definitely. Let's get into it.
Cool. So let's start with the why. Why is this robust instruction following so critical in the real world? You touched on it, but let's flesh it out.
We'll think about practical applications you might be working on. Content generation, right? You need specific style guides, keywords, factual constraints. That's multi-instruction following.
Sure. Or automated workflows.
Exactly. Integrating dozens of business rules, compliance standards, that requires the model to juggle a lot of constraints simultaneously.
And agentic systems too, I guess, with memory and tool use.
Precisely. They need to remember past instructions, follow steps, use tools correctly, all under potentially complex scenarios. And what's interesting is that recent tech advances should help here.
You mean like the huge context windows? Millions of tokens now.
Yeah, exactly. Massive context windows, better reasoning over long contexts. Theoretically, you could just give the model a huge list of instructions in one go.
But the benchmarks haven't caught up to test if that actually works well under pressure.
That's the core issue IFScale is designed to address. It stress tests that high-density scenario.
Okay, so let's dive deeper into IFScale itself. You said it's a business report task.
Right, generate a professional business report. But the constraint is including a specific list of keywords.
Yes.
And crucially, they had to be included exactly as given.
So no stemming, no variations. If the instruction is customer, it has to be customer.
Precisely. Customer, not customers, not customer-centric, just customer. Literal inclusion. And the output still had to be a coherent report, not just, a list of words.
That sounds really challenging, balancing coherence with potentially hundreds of very specific word constraints. How did they ramp up the difficulty?
Systematically, they scaled the number of keyword instructions from 10, then 20, 30, all the way up to 500 in steps of 10.
And where did they get these 500 keywords? Were they just random?
No, not at all. They wanted realistic constraints, so they built a vocabulary of 500 business-relevant single-word instructions. They sourced them from US SEC 10K filings.
Ah, the annual reports from public companies. Dense stuff.
Very dense, very specific language. They filtered these words to ensure they were unique and represented a decent challenge. So a realistic, scalable set of instructions.
Makes sense. And evaluating it, how did they automatically grade whether the model succeeded?
They use a pretty straightforward method, checking for the exact keyword inclusion using regex matching, but with wildcards enabled to be slightly forgiving on punctuation maybe.
Okay, and what if the model just gave up or produced garbage?
Good point. They built in retries. If the model outputted just a list of the keywords or refused or generated something totally incoherent, they'd give it another shot. This way, they focus the scoring on actual usable report outputs.
Smart. Okay, now the juicy part, the results. They tested 20 models from 7 big providers, Gemini, O3, GPT, Claude, Llama, Grok, DeepSeek, Quinn. A real who's who. What were the big picture trends?
Well, some things align with expectations. The reasoning models, often marked with an R in the paper, generally did better than the general purpose ones.
Right.
They could often maintain near perfect performance up to maybe 100, sometimes even 250 instructions, which is quite impressive.
And newer models beat older ones? Bigger beat smaller?
Generally, yes. Newer generation models tended to outperform older ones, and larger parameter models typically outperform their smaller counterparts. But not always.
Ah, okay. Tell me about the outliers, the surprises.
There were definitely a few curveballs. Grok 3, for example, its performance was surprisingly close to O3, one of the top reasoning models, especially at the 500 instruction mark. And it achieved that without being run in a special reasoning mode.
Interesting. Any others?
Yeah, Claude 3.7 Sonnet actually did better than the newer, supposedly more powerful Claude Opus 4 and Claude Sonnet 4 at that maximum density.
Really? So newer or bigger doesn't automatically mean better for this specific stress test?
It seems not, at least not universally. Then there was DeepSeek R1, classified as a reasoning model, but it kind of underperformed compared to others in that category.
And GPT-4o, the latest and greatest from OpenAI at the time.
That was maybe the biggest surprise. GPT-4o showed surprisingly weak performance on this benchmark. Its accuracy dropped off really quickly, more like you'd expect from a much smaller model, like GPT 4.1 Nano.
Huh. Okay, so lots of variation. The paper then talks about these 3 distinct patterns of performance degradation. Can you walk us through those? They sound important.
Yeah, they really help categorize how different models react to the increasing load. The first one is threshold decay.
Threshold decay, okay.
This is where performance stays high, almost perfect, up to a certain point, maybe 150, 200 instructions, depends on the model, and then it suddenly drops off quite sharply. Often the variance, the inconsistency, also increases dramatically at that point.
So like they hit a cognitive cliff.
It's exactly a hard limit. Top reasoning models like Gemini 2.5 Pro Preview and O3 showed this pattern. For you, as a developer, it means you need to know where that threshold is for a given model in your application. Pushing past it is asking for trouble.
Got it. What's the second pattern?
That's linear decay. It's much simpler. Performance just goes down steadily and predictably as you add more instructions, right across the range from 10 to 500.
Any examples?
Models like GPT 4.1, and interestingly, that high-performing Claude 3.7 Sonnet show this more linear decline. It's maybe more predictable, if less spectacular initially.
Okay. And the third one sounded pretty brutal, exponential decay.
Yeah, that's the one. A really rapid, steep drop in performance almost immediately, even with just a few dozen instructions. Then it levels off, but at a very low accuracy floor, often just 7% to 15%.
So they get overwhelmed super quickly.
Right. Models like Claude 3.5 Haiku and Llama 4 Scout showed this kind of pattern. It suggests their effective capacity for handling multiple instructions simultaneously is just much lower from the get-go.
This discussion about decay naturally leads to thinking about reliability, or variance. How consistent are these models as the pressure ramps up?
That's another key dimension. The variance patterns tell their own story. For the top performers, the ones with threshold decay, their variance tends to steadily increase as they approach and pass their threshold.
Meaning they become less reliable even if their average score is still okay?
Precisely. Their average might still be high, but individual results get more unpredictable. Then you have the mid-tier models. They often show a peak in variance somewhere in the middle range, say 150 to 300 instructions.
Like an unstable zone.
Kind of a critical capacity zone where they're really struggling and performance becomes erratic before it collapses more consistently at higher densities.
And the worst performers, the exponential decay ones.
Interestingly, their variance often decreases almost immediately. But that's not good news.
No, I guess not. It means they're just consistently bad.
Exactly. They're overwhelmed so quickly that they consistently fail, leading to low variance because the outcome is predictably poor.
Any anomalies in the variance data?
One stood out, Llama 4 Maverick. It showed abnormally high variance across the board. The paper suggests this might point to potentially different or maybe less stable internal mechanisms for processing instructions compared to the others.
Fascinating. Okay, let's shift to the order of instructions. You mentioned the primacy effect earlier. Can you explain that a bit more? How does it play out?
Sure. So the primacy effect is just the tendency for models to do a better job with instructions that appear earlier in the list you give them.
Makes intuitive sense. Put the important stuff first.
Right. And the study confirmed this happens. But the pattern was really intriguing. At low numbers of instructions, the effect is minimal, not much bias. Then it peaks right around that 150-200 instruction mark. That's where models are starting to feel the strain. And they seem to selectively prioritize those early instructions more strongly.
Okay, so the bias gets stronger when they start struggling, but you said it diminishes later.
Exactly. And this is the counterintuitive part. At extreme densities, 300 instructions or more, the primacy effect actually weakens again. The performance ratio between early and late instructions gets closer to 1.
So putting important stuff first becomes less effective when the model is totally overloaded.
That seems to be the implication. It suggests that once the model's attentional capacity is completely saturated, the order doesn't help as much. They just start failing more uniformly across the board. It points towards a kind of universal attention limit.
Wow. That feels like a really fundamental insight into how these models handle cognitive load. Okay, let's talk efficiency. Accuracy is one thing, but speed latency is crucial for anything real-time.
Absolutely critical. And the latency trends were stark. The reasoning models, the ones that often had higher accuracy under load, they paid a price in speed.
How bad was it?
Pretty bad in some cases. O4 Mini, for instance, went from about 12 seconds at 10 instructions to, get this, over 436 seconds at 250 instructions.
Wait, 436 seconds? That's over 7 minutes for one response.
Yeah. Imagine deploying that in a chatbot. 7 minutes of silence. It's just not practical for many applications. O3 also showed significant latency increases.
And the general purpose models.
They tended to be much more stable. Claude 3.5 Haiku, for example, barely budged its latency, stayed around 9 to 11 seconds across the whole range. Much more predictable.
So there's a clear trade-off. How did this affect the overall efficiency picture, like accuracy per second?
Well, when you calculate that accuracy to latency ratio, it drops for all models at high densities, as you'd expect. But the ranking changes quite a bit compared to pure accuracy.
Who comes out on top for efficiency?
Interestingly, it's often the faster, sometimes smaller models. Grok 3 Mini, Gemini 2.5 Flash, QFD 4.1 Nano, they achieve some of the highest efficiency ratios. They deliver more correct instructions for the compute time involved.
So the takeaway for developers is,
you really have to balance your needs. If you need absolute maximum accuracy on a complex task, maybe a slower reasoning model is okay if latency isn't critical. But for large-scale, time-sensitive stuff, a less accurate but much faster model might be the more efficient practical choice. There's no single best model. It depends heavily on the use case constraints.
Makes sense. Now let's zoom in on the errors themselves. When models fail, how do they fail? The study looked at omission versus modification errors.
Right. Omission error means the model completely failed to include the instructed keyword. Modification error means it included a variant like managing instead of the instructed management.
And what was the dominant failure mode, especially under high load?
Overwhelmingly omission. As you increase the instruction density, models just start dropping instructions entirely. Modification errors become much less frequent in comparison.
So they don't even try to get close, they just skip it.
For many models, that seems to be the default failure mode. Llama 4 Scout had an omission to modification ratio of nearly 35 at 500 instructions. That means 35 omissions for every one modification error. Llama 4 Maverick and Claude 3.5 Haiku also showed a strong bias towards just dropping instructions.
Are there exceptions? Models that try harder to modify?
Yes, the reasoning models like O3 and O4 Mini tended to maintain lower OM ratios. It suggests they are perhaps trying harder to satisfy the instruction, even if it means using a variant rather than just giving up.
Any other interesting findings there?
Gemini 2.5 Pro was unique. It was the only model whose OM ratio actually decreased at higher densities. It seemed to try harder to approximate or modify rather than omit as the load got really heavy. Quite different behavior.
That is interesting. Okay, another angle. Does focusing so hard on following all these keyword instructions negatively impact the main task, writing a coherent report?
That's a really important practical question, and the results here were actually quite encouraging for the most part.
Oh.
Most models managed to maintain pretty high coherence in the business reports they generated. Even as the instruction density went way up, the reports didn't suddenly become nonsensical or only dipped slightly in quality.
So they can juggle the instructions without totally sacrificing the core generation quality.
It seems so for many of them. They strain, yes, but the fundamental ability to generate plausible text holds up reasonably well. It speaks to the robustness of their core generative capabilities.
But you said for the most part, were there exceptions here too?
Yes, O3 and A4 mini again. They showed more noticeable declines in coherence scores, sometimes dropping below what the evaluators considered a plausible business report threshold.
Any idea why?
The paper suggests a possible link to their output length. These models tended to produce shorter reports. At 500 instructions, if your report is only, say, 1,500 tokens long, that means nearly 1 in every 3 words has to be a specific keyword. That puts immense strain on coherence.
Right, that would be incredibly hard to make sound natural.
Exactly. Though interestingly, Grok 3 also produced relatively short reports, but managed to maintain high coherence scores. So output length isn't the whole story, but it's likely a factor.
Okay, one last specific area. Did explicitly telling models to reason harder actually help? What about those thinking modes some models have?
Yeah, they tested this. They found some evidence that using a higher reasoning effort setting, like the high setting available for O3, did provide moderate performance improvements, especially at those challenging high instruction densities.
And the thinking modes?
Similar story. Enabling a thinking mode on hybrid models like Claude Sonnet 4 and Claude Opus 4 also seemed to give a moderate boost when handling lots of instructions.
So these explicit mechanisms aren't just marketing. They might actually help the model structure its process to handle complexity better.
The evidence here suggests they can, at least to some degree, particularly under heavy load. It points towards potential avenues for improving instruction following through prompting or mode selection.
Okay, so let's try and wrap this all up. We've covered a lot of ground in this AI paper podcast. We've seen that even top LLMs really struggle with following many instructions at once, revealing these distinct threshold, linear, and exponential decay patterns.
Right, and we saw that universal primacy effect, hinting at attention limits, and how models overwhelmingly resort to just omitting instructions when overloaded.
Plus, those crucial trade-offs between accuracy and latency, the fastest, aren't always the most accurate, and the most accurate can be incredibly slow. And mostly, coherence holds up, but not always.
It's also crucial for you, the listener, to remember the study's limitations. This was one specific task business reports, one type of instruction exact keywords, one domain business English from SEC filings.
So the results might not perfectly generalize to, say, creative writing tasks or different languages or more complex, nuanced instruction.
Exactly. It's a fantastic benchmark and provides vital insights, but you need to be cautious about extrapolating too broadly without further testing in your specific context.
Definitely. So let's end with that provocative thought for our listeners. Given everything we've discussed, the struggles, the patterns, the attention limits, what does this imply for the future? What fundamental changes, maybe architectural or in training, might be needed to truly get LLMs to reliably handle hundreds, maybe thousands of complex instructions without breaking down or becoming inefficient?
That's the multi-million-dollar question, isn't it? This paper clearly shows that robust, high-density instruction following isn't just a nice-to-have. It's a core dimension of cognitive capacity for these models, and it's a dimension where even the best models show clear weaknesses. So the provocative thought for you is, where do the breakthroughs need to come from? Is it better attention mechanisms, different training objectives, new architectures entirely?
It really highlights that instruction following at scale is a frontier that's wide open for innovation, something for all of us working in the field to think about.
Absolutely. It's a critical area ripe for targeted improvements.
Fantastic discussion. Thanks for breaking down that paper with us. And thank you for tuning into AI Paper Podcasts. We'll catch you on the next one.